So hello everybody, it's a pleasure to be here today and giving this lecture around quantum chemistry in near-term quantum computers and how can we do in order to do the simulation of natural sciences. My name is Panagiotis Barkoutsos and I am based in the Zurich Research Lab working for IBM Quantum. IBM Quantum is a global effort where in parallel to the development of the hardware and the algorithms, we are also working in the development of applications and how can we simulate interesting problems using near-term quantum computers. One of these interesting problems is definitely quantum chemistry and in general the simulation of natural sciences. An outline of the talk I'm going to give today, I'm going to start with an introduction to quantum chemistry and why we consider quantum chemistry being important, and also how can we leverage the knowledge we have from the classical quantum chemistry, so from the simulation using classical computers, in order to port these applications in quantum computers and start doing more and more interesting problems. Then I'm going to talk about how we are approaching quantum chemistry in near-term quantum computers and how can we leverage the available devices that we have currently in the cloud in order to be able to simulate interesting problems. One critical point that I'm also going to talk about is how can we identify whether the solution of the near-term quantum computer is exact and can be considered accurate for chemical simulations, and how can we acquire better solutions. What do we think are the developments that are needed in hardware and algorithmic developments in order to get better solutions and start thinking of bigger and bigger systems to be simulated. Then I'm going to talk about the software that one can use, and specifically Qiskit Nature, as a module that one can use to simulate natural sciences and electronic structure problems, and I'm going to give you an overview of how this software can be used to leverage critical components of Qiskit, like Qiskit runtime, in order to be able to simulate electronic structure problems. Eventually, I want to close this lecture with some applications that go beyond the electronic structure problem and give an overview of things that can be done that are not within the electronic structure problem regime. Okay, so first things first, the first person that envisioned quantum computers as a system that can be used to simulate quantum mechanical systems was Richard Feynman. One of his most famous phrases that you would see almost in every quantum computing talk nowadays is that I'm not happy with all the analysis that go with just the classical theory, because nature isn't classical, damn it, and if you want to make a simulation of nature, you would better make it quantum mechanical. Here, Richard Feynman was clearly saying that if you want to simulate a quantum mechanical system, like for the case of electronic structure problem, you should start by doing a quantum mechanical simulation. So use a quantum mechanical device, like a quantum mechanical based device, like a quantum computer, in order to simulate such a system, and you're going to make it much more efficient and much better than what you would do with classical calculations. Among the many applications that current quantum computers have, quantum chemistry is the most prominent one. Here I list some of the applications also beyond the natural sciences. Here we also list machine learning, optimization, finance, and other natural sciences, but quantum chemistry is the one that seems to be one of the most prominent. Quantum chemistry is a quantum mechanical system, and the quantum computer seems to be a relatively straightforward match to simulate quantum chemistry. What is actually quantum chemistry, and what do we study when we're talking about quantum chemistry? In general, quantum chemistry is, in principle, in the classical computing, is simulations that are used to solve chemical problems, like the case of molecular structure, like understanding reaction kinetics and reaction rates and different pathways between the different reactions. As you see in the very bottom of the slide, I show you this is an intermediate state that one has when we're talking about how we go from reactants to products. And these are things that can be simulated quite well using quantum chemistry, classical quantum chemistry. With this in mind, one can think about quantum chemistry and why quantum chemistry is a challenge in the classical computing world. Quantum chemistry is a challenge in the classical computing world because of the exponential scaling of the problem. Solving the interacting fermionic problem at its core is one of the most interesting challenges in computational physics and high-performance computing. The exact electronic wave function expansion for a system of n electrons that are going to be expanded in m basis functions, also called orbitals, scales exponentially. This means that when you're starting with m basis functions, orbitals, and you want to distribute n electrons, the number scales with a factorial according to the formula that we have down here. In order to get a feeling of what this formula means is that one can think that there are 10 to the 12 different possibilities to distribute 21 electrons in 43 spin orbitals. And this is a system of a relevant size, but still it's not the system that we want to tackle. It's a significantly smaller system than what we want to tackle in interesting cases. So with this in mind, people in the classical quantum chemistry world started developing methodologies that can really give us results in the price of some approximations that need to be applied. One of the most known approximations is the Hartree-Fock approximation, which is on the very left of the plot that we have here, which is a mean field approximation where you actually have a scaling that is quite good and allow you to simulate significantly big systems. But this loses a lot of the good properties of quantum chemistry and cannot really simulate and give exact solutions. For these reasons, people started developing theories like the Moller-Plesset perturbation theory, MP2, order 2 or 3, respectively, and these were much more costly, arriving to the coupled cluster theories, which are considered to be the gold standard. Coupled cluster with single, double, and perturbative approximation of the triples is considered to be the gold standard that will give accurate solutions, but the systems that can be tackled in this level of theory are very small ones. So there are also the first principle calculations like DFT, which are also suffering from the difficulty of finding the right functional for every system, but these are methods that in classical quantum chemistry are used to give approximative solutions. All these approximations have been derived to break the exponential scaling that we discussed before and need significant computing power in order to simulate bigger and bigger systems. These are developed within decades and have significantly played a good role in quantum chemistry and allowed people to simulate and do a lot of breakthroughs in terms of reactions and in terms of understanding how the molecules work and what are their properties. So now, why quantum chemistry is important? In principle, we need quantum chemistry in order to simulate industrial processes, in order to understand catalysis, in order to do carbon dioxide sequestration, photochemistry, among many other very interesting applications that one have in the industrial processes. At the same time, one can think about chemistry, biology, and medicine, where machine learning starts to play a significant role nowadays, that one can combine electronic structure calculations with machine learning, for example, for drug discovery. In general, what we use as a benchmark is that we want to have electronic structure calculations that can provide a more accurate description than the classical methods that I mentioned before. Here, you see one of the phrases that Alanis Purguzik, when he was in Harvard, mentioned, and he said, doing chemical simulations in a quantum computer would be like putting on a new pair of glasses and seeing the world of chemistry anew, sharp focus. This really gives us the idea that a chemist can start thinking of quantum computers as a new method to simulate molecules and as a new way to learn and leverage the functionalities of these molecules in a different way. So, what kind of problems are we interested in, and what do we want to measure out of these problems in order to simulate chemical systems in near-term quantum computers? One of the problems that I already mentioned and is quite important is the electronic structure problem. Here we want to measure the ground state and the excited states. We want to know what's the energy, and in principle we want to be able to construct the states in a quantum computer. And by having this, we are able to measure the different properties of the molecular system. Later on in this lecture, I'm going to discuss in more details about the different properties and give you also some of them. Then we want to be able to understand chemical reactions, and we want to be able to simulate quantum and classical dynamics of different molecular systems. Then, beyond electronic structure or combining electronic structure with machine learning and optimization, we want to be able to tackle other interesting applications in the natural sciences domain, like material design and protein folding. Okay, so what is the input of the problem and how do we map it in a quantum computer? Okay, this is a really interesting question in the sense that one needs to think, how do we describe molecular systems? What do we do in quantum chemistry in order to have the definition of a molecular system? And what we do is that we start by writing the fermionic Hamiltonian in the second quantization formalism. We're using creation and annihilation operators as the one that you see here, denoted as alpha, alpha dagger and alpha. And we're using 1 and 2 body integrals, which is the HPQ and HPQRS. And with this Hamiltonian, we're able to define the system and we're able to describe exactly the properties of the system. A quantum computer is not capable of understanding these fermionic relations that happen here, especially in the formalism that we have here. And what we do is that we need to map it into a qubit Hamiltonian expressed in Pauli spin matrices, in Pauli operators, which is the ones written here. You see that you start from a fermionic Hamiltonian, you go through a process that is called fermion to qubit transformation. I'm going to talk in details a bit later about it. And you express it into a qubit Hamiltonian that can be directly measured in a quantum computer. The way that the quantum computing simulation works is that we are using the circuit model. The circuit model starts from the 0-0 state that is easy to prepare in a quantum computer, applies an operation creating a final state. And from this final state, you can either start by doing dynamics, which is the time propagation of the system, or you can start measuring different observables. If the observable you are measuring is the Hamiltonian that I mentioned before, then what you are measuring is the electronic energy. So in principle, and here you have the electronic structure energy, so the energy of the molecular system, and by optimizing the unitary U that creates the state psi, you are able to construct the ground state and then measure it. I'm going to talk about details on this exactly in the next slides, but in principle, what is important is that this circuit model is based on hybrid quantum classical algorithms. What is a hybrid quantum classical algorithm? In principle, in any scheme that is quantum classical, we're trying to leverage the good properties of a classical computer and the good properties of a quantum processor. We're trying to find the advantages of the one and the advantages of the other and combine the two in order to make an efficient simulation of a molecular system. The two arrows that you see here, in principle, is a classical feedback loop where we're providing information from a classical processor to a quantum processor in order to generate the trial wave function, and then we return back the energy and we use the classical processor as an optimization machine that allows us to reiterate and go until we converge to the ground state of the system. What is the advantage of using a hybrid quantum classical scheme in a near-term quantum computer and not using a fully quantum scheme? In principle, the main advantage lies in the fact that by using hybrid quantum classical schemes, we can start using short-depth quantum circuits that can fit in the properties that our current quantum computers have, like the coherence time. At the same time, we can use these hybrid quantum classical schemes to improve on the best classical estimates and start constructing non-classical trial states. At the same time, we can store the quantum state that we have created by the unitary U that I mentioned before with exponentially fewer resources, and then we can eventually measure different observables on this particular state without the need of storing the full state in a classical computer. In general, the way that this hybrid quantum classical scheme works is that we start with a fermionic Hamiltonian, we map it to a qubit Hamiltonian, and then we use the variational quantum Eigensolver as a most known algorithm for the feedback loop that I mentioned before, and then eventually measure the ground state energy and the different properties that we are interested in. The way it works is that a classical computer is responsible for updating the set of variational parameters theta, which are eventually mapped down to qubit rotations. And this happens via classical optimization routine. Then the classical processor, so the CPU, proposes circuit parameters that are being transferred to the quantum processor that generates the states. Then we are measuring the different Pauli strings and then return. And then with the classical post-processing, we are constructing the full energy for this particular set of parameters. We are returning back this set of parameters to the classical processor, and with the classical optimization routine, we are iterating it until we converge to the system. If we want to see it a little bit in a more mathematical way, the fermionic Hamiltonian that I mentioned before is the one described on the top left. And here we have quantities like the one-body and two-body integrals that I'm going to talk about later on. And then we're having the electronic structure Hamiltonian. Then we are measuring the expectation values of all the Pauli operators, all the PIs, on the particular state psi that is based on the set of parameters theta that was proposed by the classical computer. And then classically we sum all the energies that we know that are bounded from below by the energy of the ground state. This is the variational principle that allows us to follow this optimization routine, and by reiterating until we converge to a minimum value of the quantity epsilon of the energy, then we're adjusting the parameters until we minimize, and we know that if we eventually converge to the global minimum, we have converged to the ground state of the system. And then the solution that comes out of the variational quantum eigensolver is in principle the set of parameters theta that correspond to the ground state. So when you're using these theta opt parameters, you're able to construct in your quantum circuit the ground state of the system and then measure different observables on this particular state. There are still many things in the variational quantum eigensolver that one needs to consider and one needs to optimize in order to be able to make it more efficient and actually make it successful throughout the whole optimization routine. In the fermionic Hamiltonian space, the first question that poses here is that can we start thinking of transferring more complexity of the problem directly to the fermionic Hamiltonian? Can we use schemes like multi-configuration or transcorrelated Hamiltonians in order to have more information on the fermionic Hamiltonian that would significantly reduce the requirements of the quantum circuit in order to get the ground state? One can think of this as a way to construct an easier ground state that can be easier be described by a quantum circuit and transferring this complexity down to the fermionic Hamiltonian. Then, on the qubit Hamiltonian level, can we find different mappings that are going to reduce the number of Pauli operators that we need to measure? Can we find ways that we can exploit the different symmetries in order to reduce the qubit requirements? And can we actually make it in a way that we can efficiently measure with significantly less resources the qubit Hamiltonian? On the quantum circuit level, where we're actually preparing the trial wave with the trial state, here it is important to mention, and I think that there will be another lecture related to this, that the way that we're generating a trial state plays a critical role. If you want to describe a trial state, you can either use classical quantum chemistry methods like the unitary coupled cluster that we mentioned before, or you can just generate a trial wave function based on arbitrary rotations in the different qubits and the two qubit operations. And in this way, the set of parameters theta play a role of constructing this trial wave function. The way that one constructs the ansatz is a critical component of the literature nowadays, and there are many proposals on how can one reduce the overhead in terms of circuit depth and can keep the minimum circuit depth with the possibility to describe the molecular system well enough and accurately enough. Then, On the measuring of the expectation values, depending on the problem, one can think of different aggregation methods and different aggregation functions that can be used to go beyond quantum mechanical quantities. This is something that is not directly related to electronic structure problem, because in the case of electronic structure problem, the aggregation function is the mean of the different sorts, and this we know because it's a quantum mechanical observable, the energy. But for the case of non-quantum mechanical quantities, one can think about it. Then for the calculation of energy, we need to think of techniques that can allow us to mitigate the different errors. This is quite important, and this is a very active field of literature about error mitigation and what people do in order to get significantly better results. Then, on the adjust of the parameters and the classical feedback loop for updating the variational parameters, the need of a good optimizer that is going to allow us to do good simulations on a noisy environment that are robust plays a really important role. The corrugated surface of the energy profile based on the variational parameters leads many times into local minima and being stuck in places in the surface that are difficult to be handled by classical optimizers. The need of robust and well-behaving optimizers is quite important. Eventually, one problem that we have in the variational quantum Eigensolver is what are we going to do with the solution? Okay, we did the full optimization routine, we went through all the steps, we were able to get the results that we were looking for, and now we have the set of variational parameters that can describe well the ground state of the molecular system of interest. And now what do? How do we measure different quantities? How can we extend this algorithm in order to be able to simulate more and more elaborate systems and more elaborate observables? So this is a summary of the variational quantum Eigensolver and the different challenges that one have when one wants to use this hybrid quantum classical scheme for the simulation of molecular systems. Now let's see a little bit more what is the fermionic Hamiltonian that we have and what are the different commutation relationships that fermions and spins are using and how can we actually go from one to the other. The first thing, in order to be able to describe the fermionic Hamiltonian we discussed, is the solution of the Hartree-Fock calculation in order to get the one and two body integrals. The one and two body integrals come from classical quantum chemistry codes and can be calculated in most classical codes quite efficiently. These are routines that exist since a few decades, and this can be efficiently calculated using classical codes. And we can also do it directly in the Qiskit nature, where we are calling classical codes to give us these quantities. When we have the one and the two body quantities, we are able to calculate the we're able to map the creation and annihilation operators into Pauli matrices. You see that the fermions are following different commutation relations comparing to spins, that are the qubits. And you see that you can go from the one to the other using different mappings. Examples of these mappings are Jordan-Wigner, Bravi-Kitaev, parity mapping, Bravi-Kitaev superfast encoding, and there are also many other mappings that are proposed in the literature that one can use. The most known one and the most that was developed in 1930s is a Jordan-Wigner transformation, where you start with the creation and annihilation operators and you map them to spin matrices according to the form that we have on the lower left of this figure. The important is that when you're constructing your qubit Hamiltonian, the number of terms scales order n to the 4 after the mapping. And this is quite important because when you start from an electronic structure Hamiltonian and you need to measure a qubit Hamiltonian in a quantum computer, you need to have a step that can be done efficiently classically as a pre-processing step, and then measure a Hamiltonian that can be understood by your quantum computer. So, knowing this Hamiltonian, one now can think of different approximations that can be done in order to reduce the measurement requirements, the circuit depth requirements, and how can we actually do some pre-processing steps in order to make it more efficient and easier for a quantum computer to simulate it. I'm sorry for this. Okay. So reducing the resource requirements and start simulating. Currently, we are facing limitations in terms of circuit depth that can one use a quantum computer for, and we want to be able to reduce the number of qubits and eventually the circuit depth that we need in the near-term noise intermediate scale quantum computers. What we want is that we want to be able to fit longer circuit in significantly we want to be able to fit longer circuits and more qubits in order to simulate more and more interesting systems. But what we can do is that currently we can do a limited number of qubits and a limited circuit depth. So the first step that one can do is that we can reduce the active space around the so-called Fermi level. One can think of using the orbitals that are closer to the occupied and the virtual space and start doing excitations only between these orbitals. The ones that are very deep in the that are very close to the core can be considered inactive, and the ones that are very far from the Fermi level can also be considered inactive. In this way, one can carve an active space that would significantly reduce the requirements in terms of qubits, considering that each of these orbitals requires one qubit to be mapped. And then what you do is that you are reducing your system to significantly less molecular orbitals and then make this calculation much easier. There are much more elaborate schemes that one can consider. At the same time, if you want to use the unitary coupled cluster, which is a well-defined classical quantum chemistry technique, one can also reduce the different excitations that play a significant role in the circuit depth and go with significantly lower requirements for gates in the quantum computer. Then the solution of the problem. This is quite important. The solution of the problem, in principle, is that the set of the variational parameters that we discussed before. If you plug these variational parameters straight on the circuit, you're going to construct a state that's going to be an approximate state on the ground state. In the ideal case scenario that you don't have any noise and that you don't have any local minima and that your algorithm is fully converged, you're constructing the exact ground state. But for most of the cases, due to sampling error, due to inaccuracies from the optimizer, due to noise and everything, what you're constructing is that you're constructing an approximate ground state. What you want is that you want to be able to calculate the Born-Oppenheimer potential surface. On the left, for example, here we have the lithium hydride molecule. On the left, we have the ground state energy. On the right, we have the dipole moment as an observable that one can measure. And what you want is that you want to be able to produce curves like the ones that you see here. You want to be able, the difference between all the points in that interatomic distance are just different 1 and 2 body integrals that can be considered and can be calculated by the classical codes, as we said, and then you're just measuring different Hamiltonians and you're performing a variation quantum eigensolver. These results and the ones that you see here are done using an exact simulator. You see that for the case of hydrogen on the left, we are carving an active space by reducing the number of virtual orbitals, whereas for the case of the water molecule on the right, we are carving the active space by excluding occupied orbitals. And you see how the results are approximated. Here, you see that for the full active space, for both cases, for the unitary coupled cluster ansatz, you can get results that are very good and very accurate. Whereas, for the case that you're having active space, you are introducing some approximations that give you difference in the order of millihartree from the exact solution, depending on the point in the interatomic distance that you are interested for. These results come from the paper that we published in 2018, and it gives you also all the definitions around the unitary coupled cluster and the exchange gates that we describe here. And you see here, these are artifacts, and the errors that come here are mainly due to not perfect optimization of the different variational parameters. You see again here the water and the hydrogen and the water molecule, and we did an ideal simulation of the systems in both cases. On the red, you see the Hartree-Fock curve. Okay. So this really tells us that the noise can play a role. Here we don't have direct noise, but we are able to capture them with the ideal case scenario. Here you can see from 2017 from the paper of Cantala, it was the first simulation in a quantum computer of different molecules, of molecules bigger than the hydrogen molecule. You see that the simulation of the hydrogen molecule, the simulation of lithium hydride and beryllium dihydride, and you see that the results are not matching exactly the ones of the exact solution. The exact solution is the one solid. Here they use 2, 4, and 6 qubits. And this is an artifact that comes from the noise. But even in the case that we have an approximate noise result, still we can measure multiple properties and observables of the system. These properties and the different observables that one can measure is energy, where you measure directly the Hamiltonian, and then you can also measure the dipole moment, the angular momentum, the particle number, the magnetization, and the forces. All these quantities are important for different types of calculations that one can do in the electronic structure regime and can play a significant role for the system of interest. They can describe well the molecular system, and all these are based on having access to the ground state. So having the set of variational parameters that can nicely map to the ground, that can nicely produce the ground state on a quantum computer. The only thing that changes is the quantities and the Pauli strings that you need to measure in order to get all these quantities directly. Now the question that comes, and this is a natural question, is the solution exact? And can we do something in order to make it better and more accurate? There is no guarantee that the chosen ansatz will take you to the ground state of the system. This is definitely something that one needs to take into account and can play a significant role. The reason is that the chosen ansatz can either be not expressive enough, so this means that cannot create the ground state with a set of parameters that you are providing, or the ansatz is stuck into a local minima, so the optimization routine does not allow you to go to the right place. At the same time, there is a chance that the ground state cannot be described by the variational ansatz that you chose. In order to do this, you can start thinking about Hamiltonian-inspired ansatzes that constrain the different sectors of the Hamiltonian in order to map them closer to the right solution in the right sector of the problem that you are interested in. Then you can also think of making the ansatz more rich and increase the circuit depth that is needed in order to be able to simulate it better and be able to have higher expressivity. Then, in general, the problem of finding the ground state is very difficult, and in most of the times you will not be able to capture it without paying some thinking. There will be significantly more information about this in one of the upcoming lectures, and you will hear more about it. The question again comes, can we make the solution better? What can we do in order to make the solution better? And what can we leverage from the knowledge that we have in terms of algorithms and in terms of different applications in order to simulate the systems in a more accurate and significantly better way? I think this would be a good point to have a first break, and we can go back to the question of whether we can make the solution better exactly after the break. Thank you for your attention, and we're back soon.